Hi, I am Molly, and I will do the talking in this tutorial because the guys creating the content thought this may make its production faster, but I am the only AI-generated part here. In any case, it's very nice to meet you. This tutorial is basically about how to test a system faster and in a more effective way than the traditional approaches might offer. We will be talking about a method called constrained path-based testing, which does just that. So, let's get started with the basics. In system testing, we compare what the system is expected to do with what it actually does when we try it. To make the testing process controlled and at least a bit effective, we write these expectations down as the test scenarios. If the system's actual behavior matches what is expected, the test passes. If it differs from the expectations, we then report a defect to fix. When the tested system is large and complex, thousands of test scenarios can be a real thing. These test scenarios have one thing in common: they are basically sequences of steps or actions that we need to try in the system being tested. So, in the upcoming tutorials, we are going to talk about these sequences. Testers call them test paths, and this name describes them perfectly. They are indeed paths through the system when we test it. At this point, it's good to stop for a while and think about what makes a well-defined test scenario. As we explained, its core is a test path. Each step of the test path can have an expected result, or a test scenario can have this expected result summarily. The expected result is what we check in the system under test. If the actual behavior doesn't match, we report a defect. Then, we also need to define an initial state in which we start a test path. A test path starting in different initial states of the system can obviously lead to different results based on the initial state. To give a trivial example, a test path can be a sequence of steps leading to buying the cart in an e-shop. The result will differ if the cart is empty, full, or the user is even not logged into the system. During the tests, we usually set these preconditions by using of defined testing data. Even for a relatively simple system, you can have a lot of possible test paths. And a lot of test paths means long and expensive testing. In the absolute majority of the projects, we can't afford it. As everyone is aware, budgets and deadlines for testing are generally limited. So the goal is to find test paths that would find the greatest number of relevant defects in the system in the shortest time. Preparing these paths for maximum effectiveness and doing so quickly is also crucial because the creation of test scenarios is also included in testing time and budget. The first option to create the test paths is a manual one. First, the test analyst reads and tries to understand the design documentation of the system, if it exists, of course. This documentation could be a written description or schemas, UML typically. Then, the analyst identifies test paths in the system. This manual way of doing test design can have several drawbacks. For instance, it takes time, and time means money. Also, mistakes can be made in the test cases because the test analysts may be tired or may have misunderstood the design documentation. And this design documentation is usually obsolete and out of date. Also, it might be incoherent and some parts may be missing. So, this process would not lead to the best test paths that would test the system effectively. As a result, it's very likely that the test cases will contain duplications, which may make the testing less effective. Also, it is very difficult to document what parts of the system are covered by tests. Take this situation, for example. A manager asks, "How are you covering the system with your tests?" The analyst answers, "We have created 70 test paths, so I think it's well covered." The manager then says, "I am not so sure. Sorry, but this number doesn't actually tell us that much. How do you know that you have covered everything important?" To have a guarantee, we need to show that we have satisfied a test coverage level. For example, by showing that every action and transition in the system is tested at least once. When an analyst finds the test paths manually, proving that can be a time-consuming and tedious job. Another problem is that when we need to make alterations or increase the test coverage level and we design the tests in the manual way, it usually takes even more time. it becomes obvious that for testing critical systems, manual testing is not the proper way. Also, for non-critical testing, a manual approach can be relatively suboptimal. Last but not least, all this can get complicated even further when the tested processes and workflows are large. It's fair to say that there is nothing like a standard manual test design. Even in a manual test design, you can use some formal or semi-formal test design techniques, and when you use them in the right way, the effectiveness will increase rapidly. However, just splitting design documentation text to test scenarios is a strong anti-pattern to avoid. So let's pause here for a second to explain why you should avoid doing this. Usually, the design documentation of a system under test doesn't have a uniform level of detail or quality. Some analysts add a greater level of detail and quality to the descriptions, whereas others may not. Not a surprise, that's life. Additionally, some parts of the documentation are finished by the time the test design starts, while other parts are not. That's also a very natural thing, as all the phases of the software development lifecycle are usually prolonged. Or the investor needs to decide on certain things, and these decisions can get postponed. So even if a lead analyst tries hard to consolidate the documentation and to make it uniform, naturally, different parts of the documentation may have a different level of detail and completeness. So, what happens if we just split this documentation into test scenarios? Parts that are rich in detail and well described will be covered by a number of test scenarios, whereas parts that are not so well elaborated are simply not covered by tests as well. Now look what happens. Various statistics show that from 60 up to 80% of the defects are caused by incorrectly defined requirements or weak specifications. Naturally, the parts of the system that are poorly specified will be much more prone to defects than those that are well specified. And we test the parts that are full of defects by using just a few test scenarios, so most of these defects remain undetected, and we end up wasting our effort intensively testing the parts where the likelihood of the defects is much lower. That's far from ideal, but automated test design can help greatly to avoid such ineffectiveness. So, let's explore how it works. In automated test design, we create a model of a system under test. The model usually focuses on certain aspects of the system. In our case, we model processes in the system. These models are based on an underlying mathematical structure to add an exactness that is essential for the task at hand. In our case, we are going to use directed graphs, so if you don't recall what they are, have a look at the link below this video. Sometimes we can directly transfer design documentation to the model. Typically, if the system processes are captured by UML activity diagrams, we can convert them to the process model, which is pretty straightforward. In other cases, we may need to create a model manually. Most commonly, the system model is created with a specialized model-based testing tool. We will talk about how to create the model later in this tutorial. When we have a model in place, we need to decide how strong the tests need to be. This is formalized by a test coverage criterion. We will talk about test coverage criteria later. They are usually available as options in model-based testing tools. Then, both the model and test coverage criterion are inputs to a specialized algorithm that is part of the tool and that computes test paths. Because this problem is relatively complex mathematically, most of these algorithms are AI-based nowadays. Then, you can see computed test paths in the tool. Better tools allow you to visualize the test paths directly in the system model and, of course, to export them to elaborate these paths further into more detailed test scenarios. Later in this tutorial, we will show you how all these steps are done in the CPT Manager, an environment designed and developed specifically for this job. This automated approach promises to solve the drawbacks of the manual test design. However, to make it happen, it must be done in a clever way, because there are also several drawbacks to the automated approach to be aware of. The first drawback is that model creation may take some time. It may seem that it will be worth it when we compare it to creating test scenarios manually, and this expectation is realistic. However, automated test design requires an up-to-date and accurate system model to produce relevant test paths. Hence, model maintenance, that is, keeping the model up to date with the actual state of the system under test, is one of the biggest challenges of this approach. Also, for automated test design, you may need more qualified staff. It doesn't mean that you need to hire experts in maths and AI, nor super qualified software engineers. However, the requirements are a bit higher than those needed for manual testing. Additionally, some of the generated test paths may be unfeasible in the system under test. This is because of the so-called semantic gap. The semantic gap principle is that the model is too simplified and doesn't capture all the information about the system. So, some test paths may not be accurate and they don't correspond to the actual system. This is an important issue, and we will come back to it later. Honestly, even manually designed test paths may be unfeasible in the system under test, so it's debatable whether it is fair to put it here as a challenge for automated test design specifically. However, the problem exists, so let's keep it in the list of challenges to address. To give model-based testing or automated test design more power and ability to perform much better from an economic viewpoint, we need to effectively address the mentioned problems. So, in this tutorial, we will be talking about constrained path-based testing, the main method for doing this. We will also talk about so-called model inference, another method that might be very helpful. Just a note here. When you Google model inference, you usually find a method related to neural network training in AI, but the model inference we are going to talk about here is a different thing. It just has the same name. So that's it for the initial context, and in the next video, we will go deeper into the path-based testing essentials.